Well, let's see, it's 1:20, so we can get started. Just a few announcements. So I did shoot that video over the weekend. It'll force me to put on a tie on Sunday, but I did it. And so it's on YouTube. It came out to be about 40 minutes, so maybe about almost a full class, actually. Though our full classes usually run over, so maybe about 2/3 of a class. And I covered asteroids, the asteroid belt, but also other locations that asteroids exist, including Earth-crossing asteroids and Earth-impacting asteroids. Talk about mass extinction events a little bit in there. It's kind of a fun topic. And then I switched over and talked about exoplanets. We've spent the whole course talking about planets in our solar system, which of course we know the most about these, but over the past decade or two, we've discovered thousands and thousands of worlds around other planets, and it's worthy of a little bit of our consideration. And we'll actually hit a little bit of that today. A little bit of that today will be a review from that video. But I see like 50, 60, 70 of you already watched the video, or at least parts of it, so that's good. I encourage you to do that before the exam. And it may help with homework 9 too. Homework 9, sorry, I got a burst of static there. Homework 9, this is the stuff I've been mentioning every time. It's due tomorrow at 11:59 p.m. So later than usual. You have the whole day tomorrow to work on it. And so I can squeeze in office hours on Tuesday at regular time, 2 to 3:30. I'll be holding office hours on Tuesday to help with homework 9 or anything else you may want. And then again on Friday. So not on Thursday, which is when they're normally advertised, but Tuesday and Friday this week. On Friday, it's for those of you getting ready for the final exam. And the final, as we all decided, or we all voted, and then I decided, hopefully satisfying most of you, but clearly not all, but it's going to be on Monday, a week from now, the 23rd, so near the end of the final exam testing period. And it will be available at noon. You'll have 24 hours. It's due at noon the next day. And as I've warned you, it's longer. It's probably going to be about 70 questions is what I typically produce for final exams. It's cumulative, but half the questions will be on the most recent material, lessons 7, 8, and 9, which is like a third of the lessons, but maybe about a quarter of the time we spent learning stuff. So there'll be a big emphasis on the new stuff, but everything's fair game. Study old homework, study the warm-up questions. I could have posted those by now. I forgot to. Let me make a little note here. I might do that between the two sections, so you can start studying those as well. And the old exams.
I have a question.
Yeah, go ahead.
Is today's lecture, is it going to be on the test, or is it just extra?
No, it's on the test. Yeah.
Oh, okay. Thank you.
I don't think it's in the homework, but there'll be probably a question or two on the final exam tied to this. Though today's class is meant to be a fun topic. Not that the other topics aren't fun, but this will be extra fun. So any other questions? If not, we'll move right into this. So as you can see from the slide there, today we'll be talking about ET, and specifically about, we'll be using this a lot, I'll put that back up, but specifically about SETI, Search for Extraterrestrial Intelligence. So, this semester we've talked about a lot of things. We've talked about, started out talking about how the sky works. We talked about the planets, their history, the history of their discovery, history of their exploration. We certainly talked about their properties and other things in the solar system, moons, asteroids, comets, etc. We talked a little bit about planets around other stars. Again, some of that is in that video, and I'll come across some of that, of course, today as well. And so all sorts of interesting things, and there are many more interesting things to come if you take Astro 102, where we talk about stars, galaxies, cosmology, the origin of the universe, and all that. But out of all these things, interesting things, perhaps the most interesting thing about the universe is that it harbors life. At least we know at one location here on Earth, life has developed, and quite possibly it's plentiful throughout the universe. We just simply don't know. If we're all that's out there, Carl Sagan used to say it would be an awful waste of space. It's even astronomers have a hard time grasping how big the universe is, and there's just so much of it out there that it's certainly a possibility we should entertain, that there's life out there in the universe. And part of today, what we're going to do is we're going to weigh the odds using something called Drake's equation. Now, under the topic of SETI, so many things we could talk about. We could talk about how we do these searches, how we listen for messages, what we expect the messages, how we expect them to be formatted, how we might decipher them, what they might contain, different types of civilizations that might be out there, less advanced, much more advanced. There's so many different things that we could talk about. It could fill an entire course, just the topic of life in the universe, and intelligent life in the universe. But we have less than one class left to cover this topic, so I have to be particular. I have to pick something. And so we're going to go through something called Drake's equation. So a little bit of background on that. So Drake's equation was produced by an American astronomer by the name of Frank Drake. He was a radio astronomer, mid-20th century, and he carried out the first search for intelligent life in the universe. He did it using this telescope here. This is the Tattle telescope. It's an 80-some foot diameter telescope at Green Bank Observatory. It used to be the National Radio Astronomy Observatory, now called Green Bank Observatory in West Virginia. This is the place I take students to every summer. So some of you, particularly those of you who are interested in becoming majors, you can apply for this in the spring. I'll email the class list to let you know the applications are available. And we take you here for a week. And this is one of the telescopes. It doesn't work anymore, but it's still there. Anyway, he used this telescope and he pointed it at a nearby sun-like star called Tau Ceti. He chose it because it's sun-like. It's the same color, same mass. And he's thinking, and it's nearby as well. And he's thinking, well, if there's life here around our star, maybe there's life around similar stars. And so he picked a nearby one and listened into the radio. There's all sorts of good reasons we think that the message might come at radio wavelengths, though other things are definitely possible. And he was listening for non-random signals. Stars make radio waves. There are all sorts of processes. We saw the magnetic fields around Jupiter make radio waves. There are all sorts of natural processes that make these, but it's kind of random. There's no information embedded. It's not like AM radio or FM radio or television broadcasts. They have a distinctive non-random signature because of all the information that's been embedded either in the amplitudes or the frequencies. So he pointed this large telescope at Tau Ceti and spent a lot of time listening. We say listening in the radio, but recording the radio waves and looking for structure. And there's nothing there. And so he said, this might be more difficult than I originally thought. And he went back to his office and his blackboard and sketched out Drake's equation. And there are all sorts of different forms of it, different variations. This is the one we'll use today. It's not exactly the one he produced. He had an extra term in here and maybe a slightly different order, but good enough. And the point behind Drake's equation, it's not a mathematical equation. We'll use it that way today, but mostly just for fun. There is no right answer to these questions. Well, to some of them, yes. And some of them we can make educated guesses, and some of them we have no frickin' clue. And we're just going to make some wild guesses and see what happens. We're going to treat it as a mathematical equation for fun. But really what it is an organization of the problem. What he's trying to figure out is the number of technical intelligent civilizations now present in our galaxy. And that's a crazy question. How do you just answer that question? Well, he spent some time, he broke it up into smaller, more manageable, but still many of them unanswerable pieces. And each one of these is an entire field of research. And there are people who work on small pieces of these small pieces. And maybe someday we'll have an answer. But think of it as an organization, a way to tackle a really challenging question. Now, a couple things about why he's going after this in particular. He's only considering our galaxy, not all. There are like 100 billion galaxies in the observable universe. He's only considering ours because the time it takes to send light or a message from one side of the galaxy to the other is 100,000 years. And so, we're not all the way on the edge, but we're out near the edge. And suppose there's civilization on the other side. It could be 50,000 years to get there and 50,000 years back. That's a really slow communication. If you start considering other galaxies, you're talking, millions and billions of years. We're not going to wait that long. Also, the signal degrades the farther it has to go. So he's just going to think about our galaxy, and he's not looking for how much life is out there. He wants intelligent life. And I'm sorry, my slide's still up. I've been pointing at this while I've been talking. He wants so they're in the galaxy, and he wants intelligent life and technological life because he wants to communicate with it. So his definition of technological is they have the ability and willingness to send messages across the vastness of space. Hopefully we're both using the same technique, maybe not. Maybe they're more advanced and have some other technology we haven't discovered yet, but those are details that we'll gloss over today. So let me see here. Yeah. Now I'm going to make you all take a guess, but before that, let me show how we break it down into these smaller pieces. So the first thing we're going to start with is stars. I'm going to run through each of these real quick, and then we'll double back and spend more time talking about each one, and then you'll vote on all but the first one. The first one we know from astronomy, we can just pretty much get a good number for that one. But the other ones, there's some uncertainty, more uncertainty the farther you go, and you'll guess on those. Educated guesses. Okay, so for life to exist, we think it has to be centered around a star. We don't think life's going to form in the emptiness of space. You need material, you need an energy source. So we're focused on stars. The first part is the rate at which stars form in our galaxy, averaged over its lifespan. Once you have a star, the next question is, do you have a planetary system? Again, even with the star, life's not going to form on the star, too hot, at least for life as we understand it. It's not going to form in the void of space. You need a concentration of material, building blocks, and you'll find that on planets and moons and things. So the next question is, if you have a star, what fraction of the time do you have a planetary system? And it's something we can address. Now suppose, each one of these supposes that the previous one is satisfied. So suppose you have a star with a planetary system. What fraction of these systems have what we call continuously habitable zones? We'll define it more carefully, but a habitable zone is not too hot, not too cold. It's sometimes called a Goldilocks zone. If you're too close to the star, it's going to be too hot for life to form. If you're too far away, everything's trapped in blocks of ice. We know carbon is vital for life, but it needs some way to come together. If everything's frozen in ice and rock, it's not going to happen. So there's a sweet spot, a Goldilocks zone, not too hot, not too cold. But it also has to be long lasting. We'll see some stars have a nice big Goldilocks zone, but it only lasts for a short period of time, too short for life to develop, at least as we understand it. So we'll explore this more, and then we'll put a fraction on that. What fraction of time do you have a continuously habitable zone? Then we have a number of planets, and we'll generalize. We'll throw in like moons with subsurface tidally heated oceans and outer solar system moons with methane lakes and stuff like that. But the number of worlds that are in either a traditional water-based habitable zone or these non-traditional tidally heated methane-based habitable zones. Then you get into stuff we really have no idea, moving more towards biology and society. But suppose all these conditions are met. You have a world that's in a habitable zone for a long period of time, and you have kind of the age of the galaxy to work with. What fraction of time does life arise? That's arguably the biggest question there is of all time. And personally, I think the next one is, but a lot of people say this one is. And by life, I just mean simple life, single-celled life. what fraction of the time does it develop under the proper conditions? Then once you have that, what fraction of the time, if you have simple cell life, simple single cell life, what fraction of the time does it develop into multicellular, complex, and intelligent life? I think that's a trickier question for reasons we'll get into. Then suppose you have intelligent life, what fraction of the time does it develop technological society? I think it's a mistake to assume that always will occur. And then you end with a time scale, because all of these are dimensionless numbers except the first one. That's a rate. That's a number of stars per year. So we have to end with years to end up with a dimensionless number of civilizations meeting this criteria. And the appropriate time scale would be how long you stay in that state. Suppose you do have a technologically capable civilization, capable of communicating, hopefully also willing to do so. How long do you stay in that state? It's not guaranteed you'll stay in that state forever. Some people theorize that it could be a very short time. If it's a short time, there aren't going to be many of these worlds out there at any given time for us to find and communicate with. If it's a long time, the odds go way up. Anyway, that's the outline. That's what we're going to do today. But before we do it, I'm going to show you a new feature of our e-polling tool, which is called SETI for a reason. We built it for this lecture first and generalized it for all the warm-up questions. So let's just take a wild-ass guess without going into all these things. You're just going to guess a number. Let me slide this over here. How many, let me hit the focus button again too. It's a little out of focus. Put my hand there to help it. There we go. How many technological, intelligent civilizations are present in the galaxy today? It can be a large number, a small number. If you can even put in fractions or a decimal. If you put in 0.1, that means 1 every 10 galaxies. 0.01 would be 1 every 100 galaxies. 100 would be 100 per galaxy. So go ahead and throw a number in there. And I know you've all been shy to use, some of you have been shy to use the e-polling interface over the course of the semester. Don't be shy today. We're going to use it 8 times. And so just throw your answers in there. No right answers. Let's see what you get. I'll give you another 10 seconds or so. So you got to be quick on these. Okay. You can keep putting them in, but let's see what we have here. Okay, a big mix. I'm going to stop entry, and we're going to find the class median. That's how we're going to do this. The one in the middle, crossing off the high, crossing off the low. Might be able to make this a little bit bigger so you can see everyone's guesses. You went with 1. Okay, so yeah, I'm going to put that down. That's, the experts, the so-called experts, who go through all these things very carefully, they often end up with something kind of like that. It could be 1 every couple galaxies, or it could be a couple per galaxy. Now, of course, there is 1 in our galaxy, us. And if there's only 1, that means, SETI is doomed. We're not going to find anyone else to communicate with. This would be kind of bad odds for the SETI program. I'm sorry, I'm pointing at the thing again that you can't see. But we'll make a note there, and we'll see after you've considered everything more carefully if you're more optimistic or more pessimistic. Okay. So the first one I'm not going to make you vote on. I'm going to help you on. Again, this is the rate at which stars form in our galaxy averaged over the life of our galaxy. And this is pretty simple. It's just the number of stars in our galaxy divided by how long the galaxy's been around. So does anyone know how many stars are in our galaxy, roughly? No one knows precisely, but...
At least 12.
At least 12, yes. So we have a lower bound now.
Isn't it something like 100 billion?
Yeah, 100 billion is a good ballpark number. More careful measurements over the past couple of years put it between 2 and 400 billion. So let's just say 300 billion, which would be, let's do a scientific notation, 3 times 10 to the what? What's the power for 100 billion? Anyone?
9.
9 would be a billion, so 100 billion would be
11.
11, yeah, 3 times 10 to the 11 stars. Divided by how long our galaxy's been here. Well, we've been here about the age of the universe. Anyone know the age of the universe? It's Astro 102 materials, well measured, multiple
14.
ways.
14 and a half.
Say again, 14 what?
14 and a half, I said.
Yeah.
14.6.
But how many? Is that years? Is that days?
Oh, billion
Billion
years.
years. Yep. So that'd be 1.4 times 10 to the 9, because 10 to the 9 is nope, 10 to 10. Sorry, my bad. 10 to 10 would make that 14 billion. So let's see, 3 divided by 1.4 is about 3 divided by 1.5. That's about 2. 10 to the 11 divided by 10 to the 10 is a factor of 10. So it's about 20. And that's per year, 20 stars per year on average. I'm not going to be more precise because as we get farther along, there's no precision to any of these guesses. So whether it's 22 or 18 or whatever, 20 is fine. And actually nowadays it's probably a little bit lower. We've gone through a lot of our gas. We've turned a lot of the gas into stars. There's more star formation early on, less today, but we'll just average over the lifetime. Okay, next one is fraction of stars that have planetary systems. And let me review a few things here. And a lot of this is review from the video, which some of you didn't see, many of you have seen. I'll try to be kind of quick about it. So what is the evidence for planets out there around other stars? Here is a disk of gas. This is a forming star system. A star is forming in the center. You have a disk of gas. This is taken with the ALMA radio telescope, and you can see these dark bands. This is where planets are scooping up the gas, making worlds. At this wavelength, we don't see the planets, but we see the signature of their formation. Here's another disk viewed edge on. We've seen this one before. This is Beta Pictoris. It had the kink in the disk, suggestive of the existence of a planet. And indeed, we later found it through this really kind of tricky difference imaging. The star is so bright, it makes it nearly impossible to see planets around it. But if you take multiple pictures and subtract out the star, you can sometimes see the planet. And I have a little animation. This is a different system. And this is probably the best set of images put together. The star has been canceled out, and you can see 1, 2, 3, and there's a fourth one over here. These are all Jovian mass worlds, actually super Jupiters, between 5 and 7 Jovian masses. And they took enough images you can actually see them orbiting. So we do have some images, direct images of planets. It's really hard to do. There are only a couple dozen planets we've imaged directly. Most have been through 2 indirect techniques. We've discovered thousands of planets, mostly through 2 indirect techniques. And in the video that I recorded over the weekend, I go through 4 techniques, but these 2 are the big ones. Let me review some of that. The first is the Doppler technique, and I'll do it kind of quick. There's more detail in the other video. The Doppler technique, often we can't see these planets, but they're tugging on their stars. Just like the star tugs on them, making them orbit, the planet can tug on the star a little bit. They both orbit a common center of mass. And although we may not see that planet, we can see the star inching towards us and inching away, and then towards us and away. It gets blue shifted, red shifted, blue shifted, red shifted. Just a small amount, very slow motions. Actually, that little animation I had up was depicting the Sun-Jupiter system, not to scale, but this is how much Jupiter tugs our sun. About 1 solar radius, it moves in a little circle. Anyway, in the early 90s, our technology got to the point that we could look at stars and see them moving. Here it's moving away from us, towards us, away from us. And that means there's a planet there tugging on it, making it do that. And this one you can see is a really short period, just 4 days. So this planet is really close to its star. And that helps. The closer the planet is, the more it can tug the star, and the more massive the planet is, the more it can tug the star. And this is actually a pretty massive planet, like half of Jupiter at 1/8 Mercury's orbit. So it tugged the star enough that we could see it and then figure out the planets there. Here's another example, the Upsilon Andromeda system. It looks more complicated, and it is because there are actually 3 planets tugging the star, sometimes this way, sometimes that way. And you can decipher it, and these are the 3 planets of Upsilon Andromedae superimposed on our solar system, our inner solar system for scale. And what's interesting is all three of these are Jovian mass planets. Again, gas giants in inner solar systems, something we didn't really expect. In fact, here's the first 50 discovered, and they're all Jovian mass planets, gas giants, very close to the star, something that just should not occur. And some of them are on circular orbits and some are on eccentric orbits. Anyway, as a class, we call these hot Jupiters, and we didn't expect them to be out there, but we gave it a look anyway and found their signature. And they're out there. About 10% of systems out there we now know are hot Jupiters. But early on, this is all we would find because they're the easiest. A massive planet close to the star, can tug it a lot. Given our limited technology, those are the only ones we could see. The thing about these hot Jupiters, they can't form there. We learned this last class we had. To form a gas giant, it has to be cold. You have to develop a planetesimal. You got to be out beyond where water can freeze, make a planetary core of critical mass, runaway accretion. Gas giants form in outer solar systems, not inner solar systems. So what must have happened in this 10% of cases is you had a close encounter, like Jupiter to Jupiter. Two gas giants almost hit one another. One gets flung out into deep space. We call those rogue planets. We think they're just planets without stars that have been ejected, wandering all over the galaxy. The other one gets thrown inwards, and it works its way in. And if there's still a lot of gas there, that's kind of a source of friction, slows it down, it settles into a circular orbit there. Or if the star turns on before it's settled, it will be caught in its transition elliptical orbit. Indeed, of these early ones we found, some are caught in transition and some had settled. Once the star turns on, it blows out all the gas and there's no friction, so it just keeps orbiting however it was. Again, we found lots of these early on, but now we have more capability. We can detect these massive worlds farther away. We have to watch longer, more than 4 days. It can take decades for these to go around at great distances, but we've been watching for decades now. And it turns out that about 90% of the systems out there are like our own, where the gas giants stayed out there. They may have been shifted around a little bit as they cleared out the planetesimals like we talked about last time. But that's about 90% of systems. That was the primary way of finding these. The other way of finding these, the new way, is transit method. So if that system is edge on, not face on, if it's face on, it's going around. If it's edge on, the planet will pass in front of the star every now and then, dimming its light. And maybe only by 1% or less. But we've developed these missions. The most famous one is the Kepler mission, which is done now. We launched it and it stared down our arm of the galaxy. So it looked at a whole bunch of stars down our arm and just monitored them, waiting for some of them that happen to be edge-on systems with respect to us, have their light dim just a little bit. And then you can infer things about the planet and its orbit. And Kepler found thousands and thousands of these. Most of them big gas giants because they block more of the star, making it easier to detect. But all the way down to Earth mass planets. They have a few that are in the realm of terrestrial Earth mass planets. There are new and other missions, and I talk about those in the video. There are other techniques as well that I talk about in the video, but these are the two primary ones. The point is we found lots of planets. And before I have you vote on the fraction, the question is, what fraction of stars have planetary systems? I'll tell you two things. First of all, we've done a statistical study of the Kepler data and these Doppler shift detected planets. And it seems that at least half of the stars out there have planets. And it may well be all of them. So when you vote, you're probably going to want to go between 0.5 and 1, just because that's what the information, we have data ruling out smaller numbers at this point. But one last thing, this is just an artist's rendering of the first 3 planets discovered outside of our solar system. It's a special case. They're orbiting a dead star. This is a star that reached the end of its lifetime and blew up, making a supernova explosion, destroying everything. And from the debris, new planets formed. And this suggests forming planets might be pretty easy. If you just have a disk around you, you're probably going to form planets. Okay, so I've educated you a little bit, and now we're going to vote. So again, the question is, if you have a star, what fraction of these stellar systems have planetary systems around them? So I'm going to clear the board. So a number between 0 and 1. You could do a decimal, a fraction, but you have to be in that range. I'm going to set the range 0 to 1. The farther we go, there'll be less background because we know less. It becomes more of a guess. Okay, let's see what we have here. So this one, put it in percent form. So it has to be in fraction form between 0 and 1. I'm going to stop it. I'm going to find the median. So as a class, you have collectively settled on, I can speed it up a little bit, 0.75. And I think that's reasonable. Actually, I think it's probably closer to 1. And whenever you have a planet forming, or sorry, a star forming, you're going to have a disk around it. Now, I personally wouldn't be surprised if you always get planets of some type in that disk. But it's still somewhat unknown. Okay, the next category, just to remind you, suppose you have a star, suppose you have a planetary system. Of these systems, what fraction have a continuously habitable zone? So I got to define a few things here. So habitable zone is, Goldilocks, not too hot, not too cold. And we're really talking about water. Remember, requirements for life is carbon-based, maybe silicon and other things under carbon on the periodic table, but there's so much more carbon. It's all about the carbon, really. But you need a fluid medium for the carbon to move around and come together and form complicated things. And our big two fluids are water in the inner solar system, and in the outer solar system or outer solar systems where it's colder, the water freezes, but you have liquid methane. The traditional habitable zone is focused on the water. And we'll come back and throw in non-traditional things in a second, but let's think about water. Here we have a high mass star. If you're too close to it, too hot, too far from it, too cold, but you have this nice big region. Planets form in there, you'll have liquid water. Here's a solar mass star like our sun. There's a low mass star. The lower the star is, the less energy comes out of it, cooler it is, and so you have a much tinier habitable zone. Now, a couple of problems, both with the high mass and the low mass. High mass stars, great, huge, big habitable zone, and they have a lot of fuel to burn, but they burn it much faster. We'll learn in 102 that massive stars, they live hard and die young. That's how I remember it. They may only last a couple million years. And again, that may sound like a lot, but we've been around a few billion years. A million years is probably not enough time for planets to cool down and develop life. So the high mass stars we're probably going to have to throw out. The low mass stars, they're tricky. It's a very small habitable zone. You may think, what are the odds of a planet being in that little ring? But they're more compact too. So yeah, you can have planets. The whole thing's more concentrated. You can have planets in this little ring just like you can in these bigger rings. The problem is, since they're so close to the star, you get tidally locked, which we've seen a lot of this semester. Namely, our moon is tidally locked to Earth. All moons are tidally locked to planets in our solar system for the most part. But in this case, you'd have the planet tidally locked to the star. One side would be hot always, one side would be cold always. So we call these ring worlds or twilight worlds, and we don't know if life could form on them. Life's not going to form on the hot side, too hot for liquid water. Not on the cold side, it's all frozen. There's a band right around the middle, a ring, where life could form. You don't have the whole surface to work with, just that narrow little ring. And if you're on that ring, on that equator, the sun's always on your horizon. So it's always twilight in the zone where life could form. And the winds on these worlds would be insane. the wind, the gas gets really hot on one side, really cold on the other, so the wind will circulate at crazy high speeds. We don't know if life will form on these worlds or not. So it's a question mark. Actually, let me start keeping track of these here, because there are going to be a couple more categories. So high mass, definitely not. Low mass, I'll put a question mark. Maybe life does form in that narrow ring in the twilight zone, but we don't know how likely that is. Now, how often do we get each of these types of stars? Here's a pie chart. It shows you that high mass stars are really rare, just a few percent. So the fact that we're losing them, not a big deal. Low mass stars, about half of them fall under that category of being low mass. So for the high mass stars, yeah, a few percent we're going to have to chuck, but the low mass, about half of them become highly questionable. Whether you'll have a long-term continuous zone, if that counts. A couple other categories, binaries. Half of the systems out there are binaries, where you have two stars orbiting each other. And planets can't orbit at any distance they want in a binary system. The only stable orbits are really close to one of the stars or the other, or really far from both. If you're kind of in between, you'd go back and forth and eventually get chucked out. So you can be super close, in which case it's too hot, or if that's a low mass world, you're tidally locked. Or you could be really far away, in which case you'll see two stars in the sky. You'll have a double sun, but it's going to be freaking cold because you're really far from both to stay gravitationally stable. So I'm sorry, George Lucas, you didn't quite get it right. Hoth should have had the double star, not Tatooine, and that's my nerd moment of the class. Anyway, let's put them on the list here. Binaries, no or maybe. If it's a tidally locked world, again, we're into those maybe scenarios, and that's about half the systems out there. Then we have the hot Jupiters that we talked about. Gas giants in the inner solar system. Again, they had to form in the outer solar system, have a major encounter, and be thrown into the inner solar system. And when they go across this journey, they're going to chuck out all the little Earth-like worlds that were forming there. So these would not be good systems for life, except maybe on the moons of the gas giant that they carried into the habitable zone. But we'll deal with moons separately. They're going to chuck out all the Earth-like planets. So hot Jupiters, I'm going to say no. And that, as we said before, is 10% of systems. And then the last category is the galactic habitable zone. So we keep chipping away at this number here. Here's a diagram of our galaxy. In the outskirts, there haven't been as many supernova explosions, and that's how you make carbon, the stuff that makes us. They're made in stars, the star explodes, seeds the clouds around it, they make more stars, make more carbon, they explode. To make enough carbon to make you've been through about 50 supernova explosions. And in the outskirts of the galaxy, there's just not enough carbon yet. And in the interior region, you have too many of these explosions, stellar explosions, supernovae or gamma ray bursts. The radiation levels in the interior of the galaxy might be too high for life. Now, some people would argue life will find a way. Maybe it does, but it's kind of questionable. So on here, we'll say no or maybe, and that's another 10% of stars getting ruled out. So if we put this all together, if you want to be conservative, throw out all the question marks and say, no, it's not going to happen there. Well, there's half and half of half, so we're down to a quarter, and chuck away 20-some% of that, we're down to about 0.2. So if you don't believe you can have life in the ring worlds or in the irradiated center of the galaxy, you're probably going to vote something like 0.2. But if you're more optimistic and think life will find a way on these ring worlds or in irradiated regions, you'll vote something higher. Or you may think I haven't considered all the possibilities. There may be other things out there that are detrimental to life. Maybe you vote a little bit lower. But anyway, I've educated you now. And I think, yep, it's time to vote. So again, what are you voting on? Suppose we have a star, planetary system. What fraction of the time do you have a continuously habitable zone, a place where the planet could just sit and life could potentially develop there? And we talked about all these scenarios where bad things could happen, ruining that. Okay, so next question. Go ahead.
Can you go back to the camera, please? Sorry.
This right here.
No, the other one you had, the list of the.
Oh, yeah, yep.
Okay, thank
Yep. So this one's more speculative. I've given you some information to work with. We'll see what you think.
Are we inputting like a percentage of one?
Yeah, so a number between 0 and 1. Yep. In fact, I'll set the bounds there. So you could do a fraction, a decimal. Just don't multiply by 100 and convert it to percent. Okay, you still have a few seconds to put it in. And I'm going to stop you now. Find the class median. So as a class, you said 0.22. Who said 0.22? You won't fess up, but whoever you are, correct. At least according to the class, you get the right answer. Of course, we don't really know, but I think probably something like that's reasonable. Okay, next, suppose we have one of these nice, stable, long-term habitable zones. How many worlds are in there? So let's think about that. We know less about that. So we're not going to consider these high mass stars that don't last long enough, these low mass stars that are tidally locked, just systems like our own. How many stars are in the or how many planets are in the habitable zone? So down here is our solar system, and the habitable zone where you can have liquid water, the temperature's right, is in green. And we see we have 3 worlds, Venus, Earth, and Mars, in the Goldilocks zone. Of course, other things happened. Venus is on the inner edge and had a runaway greenhouse effect. Mars is kind of tiny. It lost its heat, became geologically dead, had a reverse runaway greenhouse effect. And so maybe not life anymore, but maybe in the past. But somewhere between 1 and 3, using our solar system as a guide, which may or may not be typical, but it's much of what we know. There are some other systems that we've found with planets in the habitable zone. Kepler had a hard time finding the low mass planets, but it found some. Here's one famous system, Kepler 62, where they found 5 planets. 3 are way too close, but 2 of them are in the habitable zone. 62E and 62F are the right temperature that they could have liquid water. But what about non-traditional habitable zones? I said we shouldn't consider just being in this green Goldilocks zone. There are other places, at least in our solar system, where we found liquid water and liquid methane. Of the 7 large moons, Europa has twice as much water under the ice in liquid form, so that's a great possibility. Heated not by the sun, but by tidal forces. Ganymede had an even bigger ocean for a long time. It's a little slushy now, freezing up, but maybe. And Titan may be underground, but on the surface, we have the liquid methane. Again, you need carbon and a fluid. So this would be a non-traditional but viable possibility for life. So 3 more there. Maybe 2 if you don't want to count Ganymede anymore, if it's freezing up inside. And then also the medium-sized moon Enceladus, tidally heated to the point that water's spewing out of the surface through geysers. So if you want to count 3 planets and 3 large moons in Enceladus, that's 7 in our solar system, but that's maybe being a little too liberal. You may want to back the number down a little bit. Again, that's our system, and our system may not be typical, but it's pretty much what we have to work with, other than a few examples from Kepler. So the question is, just to remind you, as long as, suppose you have a star or planet and a nice habitable zone, what's the average number of planets, or, in that traditional habitable zone, or non-traditional, let's throw the non-traditional, like tidally heated moons, surface liquid methane, throw them all in here. Now, this is not between 0 and 1. This is a number because you can have many in a single solar system. Or if you use a decimal, if you use like 0.1, you mean 1 every 10 solar systems. If you say 10, you mean 10 per solar system. So I'm going to clear the board here, and I'll put the question back up. Average number of planets in one of these continuously habitable zones, assuming that's already there, including the non-traditional sites. I'll probably go about 5 minutes over today, but we're used to that. Okay, just a few more seconds. And we're going to find the median. Someone's super enthusiastic about worlds there. Class says 4. Okay. Now let's get into the crazy stuff we have no idea about. But I'll still give you some information to work on. Suppose everything's fine. The conditions are just great for life. That's what we've established here. What fraction of the time does life actually form? And here I just mean simple life, single-celled life. And again, many people consider this the greatest question of all time. No one knows. But I'll give you some things to think about. The first thing is the Urey-Miller experiment. A famous experiment first done in the 1950s, where they got all this, it's not just water here, but all the compounds that were in the oceans, all the atmosphere. They recreated the conditions of early Earth. They boiled the water to get a lot of that stuff up here into this chamber where they shock it with electricity. The early Earth had a lot of lightning. And that's an energy source. Maybe that energy can be funneled to creating structures out of these basic components. And then if you did form something, it would fall down and get stuck in this trap. And just like you get gunk in the trap under your sink, you take it out, dump it out, and see if you've made the, not life, but the building blocks of life. And indeed you do. It's very easy to make, again, not life, but the building blocks. There are 2 categories. You make amino acids, which are the basis of proteins, and you make nucleotide bases, which are the basis of DNA. So let's tackle those one at a time. So the amino acids, which form proteins, one form in which we see this are cell walls. In this process, just shocking the material, you could produce things that look like cells. They're not cells because there's nothing in them, but you've made the wall, the structure that holds it very easily. Here's fossilized single cells and modern day blue-green algae just to show you the similarity. The other thing you get out are the nucleotide bases, and not strands of DNA, but the adenine, guanine, thymine, cytosine. Those fall out naturally. So adding the energy, you can create the complicated building blocks. They still have to find their way together, but it's easy to make the building blocks. That's here on Earth. Now, most of Earth's water came to us in comets. NASA more recently did an experiment saying, well, comets are in space and they're exposed to ultraviolet light from the sun. So maybe this stuff forms in the comets before it even gets here. Instead of lightning, irradiate with this high energy light. And can you make proteins and amino acids and nucleotide bases? And the answer is yes. They got some material that they think is typical of comets and radiate it with ultraviolet. And indeed, you get the amino acids, you get these cell wall structures. And just to show that it actually happens, it happens in meteorites too. This is the Murchison meteorite, landed in Australia. We chopped it up and found 12 amino acids in there. So this stuff does form in space even before it gets to us. And just to broaden your horizon, people traditionally have thought about this as what are the odds of it happening on this world? But it may only have to happen once in a solar system. Suppose, we talked about this before, suppose life formed on Mars first, and then Mars got smacked and all this debris went out into space, rocks carrying microbes with it. And some of those rocks have made their way to Earth and other worlds too. And as we talked about, we sliced them open and we see things that look like fossilized microbes. Probably not, but maybe. And so the idea is maybe life only has to form once in a solar system and then everything gets just populated with debris from these early collisions. Or we can broaden it even farther. It may be that life only has to form once in a galaxy. As our galaxy rotates around, our star will move through different regions. We'll keep entering star-forming regions where stars have recently formed and material been chucked out. And some of those rocks from other stars may make it through interstellar space and land on us. So maybe it only has to happen once per galaxy. The galaxy spins in a differential way. It all gets wound up, and every region passes through every other region, with some constraints. So it may be easy to fertilize an entire galaxy once it's happened at one place. So those are the things for you to consider. We don't know how single-celled life forms, but the takeaways are the building blocks form pretty easily, and you may not have to reproduce the miracle of life everywhere. It may just have to happen once, and you can populate a whole galaxy. So given that, an answer between 0 and 1, given that all these other conditions are fine, you're in the habitable zone all the time you need, given billions of years to work with, the age the galaxy has been around, what fraction of the time does life form? So a number between 0 and 1. What is the answer to the ultimate question? You have 20 seconds. I know I'm over now, but humor me and hopefully it'll be worth it. Okay, I'm gonna cut you off there. Find the median, speed it up. To the biggest question ever, you say 20%. Okay, a couple more here. So I think the next question is the biggest question ever. And the next question is, once you have simple life, what fraction of the time does it evolve into intelligent life? And people often ask, what do you mean by intelligent life? And some people say, I don't think intelligent life's even formed yet here on Earth. And the most interesting way it's ever been asked to me is someone once said, is a pig intelligent? And I think the way to look at this is if you've evolved all the way up to something as complicated as a pig, it's not long before you evolve more complicated and more intelligent structures. Here's a really important figure to help you understand this. This is the history of life on Earth, 4.6 billion years here. The first 1.5 billion years, too hot, nothing happened. But then we had our oceans, and almost immediately we had single-celled life. Maybe we got lucky, but maybe this is telling us that's not the hard step. It happened as soon as we had temperatures low enough to have water. But then we had to wait 2.5 billion years for those single-cell life forms to become multicellular. And after that, it exploded. We got like ton diversification, all sorts of life, and it just ramps up. And here we are in the final pixel of this plot. Puts our existence in perspective. We're just passing through, and we're just a glimpse here in time. The trick to me is getting from single cell to multi-cell. If it took another billion years, we wouldn't be here. And we may still be just oceans of single cell life. So something special and rare has to happen for that to occur. Fortunately, it did happen here. So back to the voting. Again, the question is, if you have single cell life already, what fraction of the time, given billions of years to work with, maybe about 10 billion years, age of our galaxy, what fraction of the time do you develop intelligent life? Go for it. 0 to 1.
Professor, I have a question. So for the exam, what part of this class would exactly be a question on the exam?
Oh, anything in Drake's equation. I can ask you about different parts of Drake's equation. I'm not going to ask you to give me the answer to the most important question, because there's no known answer, but I could ask you what that question is.
Right, yeah, that's where I was a little confused, but that makes sense.
Yeah, the numbers we're putting in are just for fun. And we're almost done. You see we're going through them faster now. So to go from simple to complex, you say 8%. Now, suppose you have intelligent life. Doesn't necessarily mean it's going to be technological life. Let me just throw a few quick counterexamples here on Earth. Some species that some people anyway think are intelligent. such as chimpanzees. Some people think they're intelligent. Though you may argue that's our branch of the tree of life. We didn't evolve from chimps. We had a common ancestor, but maybe we represent that branch. But then you also have cetaceans, like dolphins and porpoises and humpback whales. Dolphins are smart. They've learned to speak and use, in proper context, 50 words of English. They don't say it like we do. They use clicks and whistles, but they can speak English to us. You know how many words of dolphin we have figured out? 0. So it makes you wonder who's the smarter animal. So dolphins, porpoises, humpback whales, their whale songs are very complicated. There's information in there. We can't figure it out. And these are examples of species that maybe are intelligent, maybe as intelligent as us, but clearly they're not technologically inclined. They're not going to be sending messages across the vastness of space. So just because you become intelligent doesn't necessarily mean you're going to be communicating and technological. So that's this question. Suppose you have intelligent life. What fraction of the time is it technological? 0 to 1. Survey says 6%. Okay, and now the final factor in Drake's equation, which is how long? Suppose you have a civilization in a technological state, capable and perhaps willing to communicate. How long do they stay that way? Well, opinions about this have changed with time. First, we should say, how old are we? By this definition, we became technological when we first sent a strong radio broadcast into space. Does anyone know when that was and who did it?
Can I guess?
Yeah, go ahead.
Was it at the 1936 Olympics?
That's right. Who
It
sent
was Hitler's broadcast.
Hitler. Yeah, so if there is other life out there listening, the first message they're going to get representing the human race is Adolf Hitler. That's something to ponder. And there's a great movie called Contact, based upon the book written by Carl Sagan, that I encourage you to watch. Jodie Foster plays the main character. It's really good. It's about that premise. Anyway, so that means we are 84 years old as a technological society. How long will we last? And people's opinions have changed over the years. During the Cold War, we thought not long. You become technological, you build weapons of mass destruction, you blow yourself back to the Stone Age. So we thought it would be a short period of time. But then the Cold War ended. Even though the nukes are still pointed at us, we became more optimistic and said, we'll last as long as we don't get smacked by an asteroid. And as we saw last time, that's millions of years. We could go millions of years. Or if we can get off the planet, this is just for fun, that's the space station from the movie 2001. And the space station we actually have up there, if we can get off the planet, again, we just sent 4 astronauts up there yesterday, but really to other planets like Mars, or to planets in other star systems eventually. If one planet gets wiped out, then humanity continues. So, if we can get to the point where we colonize other places, it's essentially the age of the universe is how long we'll last. We'll evolve into something more than human by that time, but 10 to the 10. So when you answer this question, think not in years, but in powers of 10. When I do this in class, someone may say 1,000 and the person next to them said 1,100. And really those two numbers are the same. Are we talking about 1 year, 10 year, 100 year, 1,000, million, billion, 10 billion? Think in powers of 10. Okay. So you can vote. How long does a technological civilization stay technological? So a big number of years. This is where we'll get the greatest variation. I really enjoy looking at these numbers here. Okay, I'm going to cut you off there. I'm going to find the median. As a class, you say 100,000 years. What's the smallest one here? I always like looking for that. 100. We're already 84 years in, so that means 16 years to go. A number of you said 100. So, just quit school now. If it's only 16 years, go enjoy your time on the beach once COVID's done. Just relax. Where are my slides? I've lost them. But no, don't be a fool. Stay in school. Anyway, it's an 80s reference that most of you probably don't get anymore. So let's put these numbers together and see what you all said as a class. Pull up a calculator here. And you originally guessed 1. So it's going to be 20 times 0.75 times 0.22 times 4 times 0.2 times 0.08 times 0.06 times 100,000. You're a lot more optimistic than you thought. You say there are about 1,200 to 1,300 technologically communication-ready civilizations in our galaxy today. And that means it's probably worth pursuing SETI. There's probably entities out there to think about, to meet with. Last thing to think about, this is our galaxy. There are 100 billion galaxies in the universe. So this is about 10 to the 3. That means there's about 100 trillion such civilizations in the observable universe. So we're probably not alone. As Sagan said, it would be an awful waste of space. Anyway, I'm done. Thank you for waiting the extra time. And I hope you enjoyed the semester. I enjoyed it. It was fun.
Thank you.
Thank you.
Thank you, Professor.
Thank you, Dr. Record.
Thank you.
Thanks, Professor.
Thank you.
Thank you.
Did you enjoy the semester?
Who, me? Yes, I did.
What did you
It
say
was a
the
great
name?
semester. Thank you, Professor.
Glad you liked it. Yep.
What did you say the name of Drake was? What was his first name?
Frank.
Thank you.
Thank you, Dr. Reichardt.
My pleasure.
Thank you, Doctor.